Okay, so we have all these interesting properties about graphs, but how can we represent graphs? The simplest way of doing that without actually drawing the graph is by using an adjacency list. So in this adjacency list, you have a two-column matrix or a two-column table where the first column is the vertex number, and then on the second column you write the vertices which are adjacent to that particular vertex in that row. So here you can tell which vertex is connected to what, and from this adjacency list you are able to build the graph to its full representation. And then you have adjacency matrices. So the adjacency matrix is a n by n matrix because it's a square matrix where you have that the rows represent the vertices and the columns represent the vertices as well. And then you write a 1 if those two are connected or a 0 if they are not connected. You also have incidence matrices. Incident matrices are used to represent undirected graphs. And let me go back here to generalize. When I described the adjacency matrix here, I said that you write a 1 if they're connected, 0 if they are not. But in fact, if you have multiple edges between two vertices, then you can write, instead of writing number 1, you write the number of edges that are connecting those two vertices. And then we have the incident matrix. So here you have 1s and 0s. So 1 if they are connected, 0 if they are not. Then we have the concept of isomorphic graphs. Isomorphic graphs are two graphs that can be mapped one to the other through some function f. And the concept of isomorphism is a little bit, it's not easy to explain with words. It's easier to explain with drawings. But what you have here is you have a graph G1 and a graph G2, and then you have V1 and V2. So if you have a mapping or a function f that takes you from V1 to V2, and a function that takes you from the edges E1 to E2, then you have an isomorphism. So isomorphism is a representation of the same graph using a different labeling of the vertices. In the synchronous session, we'll do exercises to make sure this concept of isomorphism is clear. Now, if I give you two different graphs, can you tell whether they are isomorphic or not? If the graphs are small, then yes, you can, or a computer can. But if the graphs are big, very large, with a very large number of vertices and edges, then this is very difficult. In fact, telling whether two graphs are isomorphic is one of the fundamental problems of computational complexity.